Yeah, hi. Good evening, everyone. Welcome to this week 5 and 6. So, today actually we are planning to discuss some programming problems from week 5 as well as the week 6. Okay, so both the week we will cover today because last week actually we didn't cover that due to that quiz one revision session or some mock discussion session. So we have total three problem from each week. So total six problem we have today for the live coding. So let me share my screen and then we can start discussion. If anyone have any query before that, you can ask. You can also share your that how was the quiz experience, the level of the quiz, any feedback. So what was the level of the quiz actually according to you? And have you received
It
the
was moderate, I guess.
moderate? Okay. Okay. Anyone feels easy and anyone feel that hard? Okay. And have you received the marks for this quiz one? That final score?
Yes,
Or it is released?
yes, it is released.
Okay. Okay. Yeah. Fine. Okay. So if there is no query, then we can proceed. Okay. So you can open the live that Replit team. Okay. I hope you have the link. So I am sharing the problem. For first, I am sharing the problem for week 5, that releasing three problem. Then we will release the another three for week 6. Okay. So I've released these three problems. Now you can refresh your page and you can get these problems from your Replit team. Okay. So I'm opening the first problem. So you know that week 5, what we have discussed, that regarding some shortest path algorithm and minimum spanning tree algorithms. So these are the two topics we have learned in week 5, and we have learned some three algorithms for shortest path, the dashed algorithm, Bellman-Ford algorithm, and Flood-Warshall algorithm, and another two for spanning tree, minimum spanning tree. So now this first problem, let's see which algorithm is suitable for this. So I'm reading the problem statement. Now just tell me which algorithm we can apply here, and you can also try to solve this. So an airline company wants to make airport to connect n cities, label from 0 to n minus 1, all across the country. Write a function airport distance map that accept a weighted adjacency list distance map in the following format. The function return the minimum distance of airport network to connect all n cities. Okay. So here some information is given. So that means one adjacency list is given. You can see this format we are using for adjacency list with the help of dictionary. So where we have the each source, okay, and for each source, that means in the graph, each vertex we have the connection in the form of destination index. So that means the connected vertex from the source in the vertex, and what is the distance in kilometer. Okay, so in this format we have this adjacency list data, and this name is distance map. A question, and this label is actually defined by 0 to n minus 1. Okay, if we have 10 cities, so the city names will be defined by 0 to 9. And in this way, question is asking the function returns the minimum distance of airport network to connect all n cities. So this information is given. So here you can see some sample input. So this 7, this number of vertices are given. So that is representing the number of city, and label will be from 0 to 6. So you can see in this in detail, this is the edge. So we have the edge information, and that means connection, and you need to find out the minimum distance of the which actually connects all the city. So which algorithms are suitable? Can anyone confirm? Which algorithm we can think for this?
Minimum cost spanning tree.
Yes, correct. Okay, so here actually we want to connect all the cities and with the minimum distance of the network. So that means we will remove, so we can apply, we can figure out the minimum spanning tree, and that will actually provide the minimum distance which actually of the network which connects all the vertices by the edge without any cycle. Okay, so here you can think about the minimum spanning tree algorithm. So you can apply any algorithms which you are comfortable. So if you know Prim's algorithm, you can apply Prim's, and otherwise you can also apply the Kruskal algorithm if you are okay with Kruskal algorithms, because both returns the same output. So here you can see what is given in the suffix code. So that means you need to write a function airport, and you are getting this WL, okay, adjacency list, and you need to write this function. All things are actually already converted into the suffix code. So that means in sample input you see that we are receiving the edge, but after that the suffix code is actually converting this edge information to a adjacency list matrix by this code. And this code we have already seen in the previous sessions. Okay, that how we convert any data graph into adjacency list and or adjacency matrix. So okay, now you can try to write the code of Kruskal algorithm or maybe Prim's algorithm. So this is a straightforward question. You need to implement that one of the algorithm. So regarding the OPP exam, so in the graph actually this week 4 and week 5. So these algorithms you should know at least one algorithm for that shortest path algorithm, at least one algorithm from that spanning tree, and BFS, DFS, and topological sort. These 5 algorithms you should at least know. Okay, so maybe some direct question may also be asked that is based on the any particular algorithms. So at least just learn one of the algorithm from each. Okay. Otherwise, some question may be asked related to the some additional task. So maybe some algorithms will be given already to you, or like dashed algorithm is given, but some additional task is required with the help of this given algorithm. So like we have discussed in the previous week. So week 4, not week 4. Yeah. Yeah, some algorithm. Suppose you are given like a shortest path algorithm based question, and where you need to figure out the path. Okay, and already dashed algorithm is given where that provide only the information that shortest distance. You can simply update that algorithm little bit, and you can just also maintain the parent information, and you can figure out the path. And this exact problem I already we have discussed in week 4 live coding this session. Okay, using the BFS parent information. So now you can start this, and then we will discuss. If anyone have any query in this, any doubt, you can ask. So I checked some the discourse forum. So maybe if anyone have some confusion regarding this OPP exam, so PDSA we have only one OPP exam, okay, and that will held at the time of OPP2 exam of the other courses, like in August next month, not this, okay, July. So we don't have this OPP1 for PDSA. Okay, so those who have joined, please open these problems on the Replit and try to solve. Okay, just practice on these questions. Otherwise, you will find OPP exam difficult. So here right now you can practice. Later you can also practice on the portal. So that is open after that 30 September. So all problems will be open for 30 September. So you can practice. You can write the multiple solution. You can check your logic. Okay. So let me discuss this Kruskal algorithm or concept. So here you can think about Prim's algorithm is little bit similar to the Dijkstra algorithm, and the code is also a little bit heavy. So what you can do, you can just try to recall the Kruskal algorithms. We have discussed this Kruskal algorithm in that opening session of week 5, and you can write the code for that. So what actually Kruskal does? So let me explain. Okay. So in Kruskal algorithms, if you have edge information, so if adjacency list is given, you can what you can do, you can that from the adjacency list you can return the edge information. Okay, so that means you can that fetch all the edge information, like which node is connected to which another node. So by that way, we will sort the edge. Suppose you have this edge like E1, E2, you can fetch this all information from the node that that adjacency list. Okay, after that perform the sorting on this edge. Sorting, so just sort these edge by their weights in increasing order. So that means the smallest weight should come at the first edge. So after this is the first step, sort. Okay, and after that we will pick the edge one by one, and we will connect that edge into our uh, initial graph. So what we will do, we will initially consider that our each node, suppose we have like 5 vertex, so v1, v2, v3, and v4 and v5. So initially we will consider that each vertex is a single component, not connected to any other vertex. So this is the concept of Kruskal algorithm. We start from like that. We initially consider that each vertex is a single component, and we will also maintain some information that is actually a component number, or we can say that component leader. Okay, we make for every component we make any one vertex as a leader of the components. So what this means, so initially each vertex have one as a separate component, so we will consider that the same vertex is a leader for that. So v1, that v2, and this v3, this information we can maintain. So v4, v5. Okay, after that, after the sorting, suppose we are getting like this e2, e4, e1, e3, e6, like this, and in this way we will pick the edge one by one. So what edge this e2 connected, so we will get the information edge of that source and vertex. Each edge will be represented by source and vertex and weight. So in this way we will pick the edge one by one, and we will connect, we will check. So what is the source vertex? So in each edge s comma v. Okay, so like here suppose we are adding that's v1 comma v2. Okay, so suppose this is a edge, first edge. So we will check what is the component of v1 in our initial condition. So we will check component of v1 is v1. What is the component of v2? Yeah, this is the v2. So if you are finding out that if the component of that source vertex and destination vertex in the edge are different, so that means that are not connected till now. So you can connect that without any problem. So that means you simply connect this. Okay. But the meaning of this, if the component of v1 and component of v2 is different, so that means if you will connect this edge, so it will not create a cycle, because both that vertices are not coming from the same component. Those are coming from the different components, so we can connect. Okay, so what happens, suppose we connect the next edge like v3 and v4. Okay, and here same things, v3 and v4 is still now a are separate components, so we will connect that. So after connecting this every edge, we will make a one component leader for each vertex, which are those are connected to this component. Suppose after v1 and v2, when we are connecting that, so component leader for this part will be the one vertex. Like we can make v1 for both, so like we can update this and v1. Okay, so that means the what is the component that leader for v1 is v1, and what is the leader for v2 is v1, same. Okay, so that means this leader is representing that how many vertices are connected to this component. Same things we can do here. So v3 and v3 we can update for the same. Okay, after connecting. So after that, suppose if we add this okay, suppose we connect this v3 and v2, then again component is different. Okay, so v3 is v3 and v2 is v1, then we can still also connect. So after connecting this, we will update the component for each. So that means we will pick the smaller leader and we will update this. So v1, and this is also v1. But if we connect this like v1 and v4, so v1 and v4, so this edge actually, what is the leader for v1 is v1. Okay, what is the leader for v5, that v4 is also v1. At any time, if you are getting the same component leader, that means you will understand that both vertices are coming from one component. If you will add this edge, it will create a cycle, so that is not required. So at that time you can ignore this. Okay, so what we are doing, we are picking the edge one by one. We are checking the component leader. If component leader are different, then we will consider this edge in our spanning tree. If component leader are same, then we will ignore the edge. This process we will do in the Kruskal algorithms. So we need to write the code for this. So I am writing the code. Okay, so what we have discussed, now we will write the same things. Those who are writing, you can also just write the first and you can move to the second problem if you have already done this. But you should know the implementation for this, okay, and also understanding. So we need to write it. What we need to compute in this, sorry, distance. Okay. Okay. So this is our required function, and inside this function, first task we have to do, we have to return the edge. Okay, so we don't know. This time we have the adjacency list, but we will return the edge from the list. So what we can do, we can just consider, we will take one list, edge is the empty list, and after that we will we will just read all the keys and we will read the edge. So for that key, okay, so for that we are reading the key, so that source vertex. Okay, so source in, because key are representing as a source vertex, so wl dot keys. So now this, and after that we will just append all the edge in the edge list. So that means edge dot append, what we will append. So this time, and one more thing, we have the source vertex in the tuple. Actually, we have the source vertex, destination vertex, and then weight. But what we will do, we will store the weight at the first place. So that will actually help us to direct sorting. So what we can do, we can use this. Okay, so this is where is that key component of. Okay, so that is append. Append. Okay, so let's do this. Source. So we have this W. W and first value, and we will write it inside the tuple. So tuple. WL dot, not dot, sorry, the source SVURC. And inside the value of this each. Okay, source we have as a key, and value we have the at the index 0, 1. 1 first. Okay, and then source, and then 0. Okay. So in this way, we are appending all these as initially. So let's see what we are getting if we are passing this.
Sir, put it 0, not 1 in the end.
So this is 0. That's correct. Yes. Or I'll remove this as okay. Okay. So edge dot append. Now we are creating a edge list where each tuple is representing first value as a weight, then source, then destination. Okay. So this is the first information, and same for each key. We will also do one more thing, and we will maintain a component leader. So we can write like a component. So see component, and this will we will make as a dictionary. And here we will create initially, so that initial part is we will make the same vertex as a component value. So that source equal to source. Why did you say error? Is anything missing? Invalid syntax. Okay, so as append open two brackets, and here one is there. Okay, so one bracket is missing. So we are initializing the component for each vertex as the same vertex. So this is the initial part, and let's see that we will sort this edge list. So edg edge dot sort. Okay, now this is the first things we have done. After that, what we will do, we will pick the edge one by one from this list, because now edge is sorted based on their that distance. Okay, after that we will run a loop. So now we will pick 3 value from this tuple, because each tuple have 3 value. So for that d comma s comma b, okay, or we can take that like u comma v. So u comma v for each s in h. And after that, we will check if the component of the each edge are not equal to. Then we will do the process. Otherwise, we will skip. So if
Sir, isn't D and V equal according to you in the append block? You have provided.
no, this is the
Source.
first value, because in
And the
you can see now in each edge, what we are storing. So this value we are storing as a destination, and second
Okay.
value we are storing as a that distance. Okay, you
That
can.
is 0 and that is 1, sir. But you have given 1 1 both in D and V.
Oh, I have already updated how it is changed. Okay, one second. It will not change. Hmm. Okay, yeah, correct. So now we will read this as and check the condition. If component of u, okay, is not equal to component of v. If this condition is true, then oh, I'm writing C syntax. Okay, sorry. Hmm. Okay, so if this condition is if that means component value of both vertex that u and v are not same, then we will do the then we will include this edge in our spanning tree. Otherwise, we will not do anything. So that means we will not write any else condition for this. So here, what we will do, we will just consider this edge in our tree, and we will update the component for the vertex. So this is v. So first thing, we will also maintain a distance. So distance for maintain a distance. So total dist equal to 0, and we will add this distance in a, for the output. So for sorry dist plus equal to this d value. Okay, and other than this, now we will read the component because the component for u and v are different. So we will read the component value for one vertex, and we will copy that component for the each vertex which are connected to this v. Okay, so in this way, so what we will do, we will just read a component like c equal to component of u we are reading here. So what is the that component leader for u? And after that we will run a loop. So that loop for like w in that wl dot is okay. If so, we are what we are looking here. So we are checking each keys, and if we have that component uh, of any keys, if the component value is equal to c, then we will update the our component value. So that means we will check if the w component of w equal to c. Then we what we will do, we will update the component of w to okay component of v. Hmm. Yeah, so this is the code. So here we are just taking the component leader. So what is the leader for u? And we are checking and which key have this leader equal to c. Okay, we will update the leader by the leader of component v. Okay, leader of v. So that means the all nodes which are connected to this v, sorry, all nodes which are connected to this u, the leader will be updated by the leader of this v. Okay, so in this way, now this loop will work. It will read each edge from our list, and it will skip if we are getting the same leader. It will skip that edge. Otherwise, it will add in our tree. So here we are just adding this distance, and after completion of this process, we will just return a this distance value. So return. So this distance actually representing a minimum that connection that is minimum spanning tree cost. So let's run this and see. That is slow, I think. What happened? Okay, let's see this on portal. This one, 4B5, B5. This one. Okay, so print airport. So for source and key dict object has no attribute key. Zero 50. See what we did. W in W3 and W. Okay, so this is also wrong. Component of B. Component of W. What is the error? Print error, if component is not equal to key error. 0,50. We are getting this 0,50. Component of U is not equal to component of V. So U in H. And let's check here this is running or not. Failed. That is on this line. The error is 1.5. Okay, so let's print first this H. What we are getting this inside the H. And this retest. A without getting any. One eighty. And this. Okay, why it is not copying? Okay, so it is getting as list, but why this is not reading? Let's revisit the code once. Let's see what is the possible issue. So as we are following a, this is fine. Component u disk 0 for source in wl dot keys. Yeah, this is okay. S dot append. So we are appending inside the S. So this is wl and source. So yeah, this is representing key. And what is the key value? So the source and okay. Okay. So wl then source. It is returning a list, and in this list, okay, yeah, so actually we have this for each key we have a list of edges. Okay. So yeah, this is not working fine. So this is not correct. Here we have to run another loop, or what we can do, we can create in a different way. So that we can use extend, and we can run it. I guess so. This where d comma at u comma v at source comma v. Okay. So for v comma a n double l at a u the source. Yeah. So what we are doing, we are creating it directly. So actually, each key have a value in the list of tuples. So there is a possibility that we have multiple tuples in the for each key. So here we are reading all the for keys. That means for each source, we are reading all the VD combinations. So that means source to V, how many edges are there. So we are reading that, and after that we are arranging into this order in our list as a tuple. So D will come as the first, this T, and source will come as the second point. So this is the source, and this will come as a destination. So in this way, we can also create this, and let's run this. Yeah, now this is working. So previously we actually we were just reading incorrectly that one tuple only. That was not correct. Now this will also pass the oops. 180. Okay. Yeah, please open your mic if anyone has got queries. Hello.
Sir, could you explain what is happening in 13 to 70 line? What is?
Okay. So that this 13 to this one.
Yes, sir.
Okay. So what we are doing in this line, actually, first thing, this is the clear. We are simply adding the distance in our result. So because we are
Yes, sir.
considering this edge in our tree, and we are adding this edge in our result. This is the main
Yes,
part you are looking for. Okay. So what we are
yes, sir.
doing, so in this graph, suppose let me copy that. I'm just making one example. So suppose we have this 0, 1, 2, 3. Okay, and we have this 4 vertex in the original graph. So like this edge are given. So we have this 1, 3, 2, 4, 6. Okay, this vertex we have. So first things, we will just arrange the all into a sorted list. So that means 0, 1 will come as a first. Next is 0, 3 will come as a second. And next is 0 comma 2. So 0 comma 2 will come as third, and this is now 2 comma 3 will come as fourth, and this will become a fifth. So 1 comma 3. Okay, so these are the sorted list of the edge. After that, what we are doing, we are simply assuming that component of each. So that means 0, 1, 3, sorry, 2 and 3. We have initially, we have just make as a component of 0 equal to 0. Okay, so that means these are the vertex, and we initially assign as a component of each node as a same node. So 0 for this, 0 for this, and sorry, 2 for this, and 1 for this, and 3 for this. Okay, so this was the initial steps. But what we are doing here, in this 0 comma that 1. Okay, 0 comma 1, we have this. So we will check that what is the component value of 0, what is the component value of 1. So both are different. So we will connect this. We will consider this edge. And after connecting this edge, what we are doing, we are looking for what is the, so we are just consider that this is a u and this is a v. So we are checking what is the component of this 0. Okay, so component of 0 is this 0. After that, we will read all the keys in the dictionary. Okay, and we will check which vertices have the same component value 0. So we will update that component value by the component value of this p. So what we'll check, we will check this as so we will check this 0 vertices. Okay, so this is now matched, yeah, 0. So we will update this value by the component value of this v. So what is the component value of this? 1. So we will update this 1. Now we will check 1. So this is not equal to 0. This is not equal to 0. This is not equal to 0. So only the updation will happen on only for this u. So now you can see that after connection of this, these both vertices have the same component value. Okay, and now suppose if we connect this vertices, next is 0 to 3. Okay, so 0 to 3. So what will happen after connecting this? So same, initially the component value of 0 is 1 and 3 is 3. Both are different, so we can connect this. So this will be connect, and after connecting this, now we will check. So we consider this as a u and this as a v. So what is the component value of u? So the component value of u is 1. Okay, and we will just revisit all the vertices. So we will check which vertices have the 1 component value. So we will check each vertices 0. Yeah, this have the 1 vertices. Now we will update this by a component value of this v component. Okay, this is 3. So we will replace this 3. And now we will check the second vertices in our graph. So this is also contains the same 1. So this will also update by 3. Now we will check this 2. This is not equal to 1. So we will skip this. Now this 3, this is also not equal to 1. So we will skip this. So after this process, you can see this is now becoming 1 component. So where each vertex they have the same component value. So in this way, after connecting the edge, we are making the 1 component value for each vertices. So that operation is performing in this code.
Understood, sir. Thank you.
Okay, yeah. So yeah, this is the Kruskal algorithm. You can learn this for the spanning tree problem. Okay. Okay. Any query? Anyone in this code? Or shall we move to the next problem? Okay. If there is no query. Now B5 problem 2. That okay. So here the problem statement I am reading. you are given a network of n nodes labeled from 0 to n minus 1. You are also given a travel times, a list of signal travel times as directed as travel times of I equal to ui, so ui, comma vi, comma wi. So this I is coming as an index. Consider this as a, this u is for I vertices. Okay, so just consider this as a the index. Okay, where ui is the source node and vi is the target node, and wi is the time it takes for a signal to travel from source to target. So this is basically a representation of the dictionary. You can see. Okay, so each vertices I, we have this information. So where the u I, okay, so also given the travel time. So so this is representing the connections. Actually, each tuple is representing this information. So source vertex, destination vertex, and the travel time. Wi is just representing a travel time. And in the context of graph, we can understand this is a distance between this source and this destination vertex. After that, write a function minimum transmission time, and we will pass this n, which is represent okay, n travel times and s that accept number of nodes in the graph n, a list travel times, so this is list of edges, and a source vertices s to send the signal. The function returns the minimum time required for the signal sent by the source node s to be received by all the remaining n minus 1 nodes. If it is impossible to obtain a signal for all n minus 1 nodes, return minus 1. So what is given in this? Suppose we have a graph, okay, in the form of graph, and this vertex is a S. This is a S source vertices, and other vertices is also connected like this. Okay. And, so suppose this is connected in this way, like this. Okay. Suppose this is a graph. Now we have the information like that S2, and suppose this node naming I'm giving that this is 0, 1, 2, 3, 4, 5, 6, 7. Okay. Now each edge is also representing a travel time. So like this is a 10, this is 1, this is 2, this is 4, this is 5, this is 6, this is 5, this is 8. Okay. So now we are sending a signal from S. Okay. And what is the minimum time required to send that signal will received by the all nodes from this S? What minimum time is required? Okay. So that is question. If suppose if any node is not connected, like if any vertex that another vertex we have 8, which is not connected. So that means if we are sending a signal from S, so that signal will not be reached at this 8. So this is disconnected basically. So we will say that that this source is not able to send the signal to all vertices. Okay, so one is now remaining. So in that case, we will return a -1. Okay, if all vertices, our signal is reached at all vertices, then we'll return a minimum time. What is the minimum time required to receive the signal by all vertices? So which algorithm you can think about? Think here. Anyone have any idea which algorithm we can use here? Yeah, hello. Any suggestion, anyone? What logic we can use here?
Dijkstra's algorithm.
Okay, so you are selecting Dijkstra algorithm, but after that, what you will do? To return a minimum time, what value actually you will return? How you will calculate the minimum time required? So first thing, you will understand that what is the meaning of minimum time is here. Okay, so we will calculate the that, yeah, correct, that Dijkstra algorithm we will use here. So we will just consider this as a source vertices, and we will apply the Dijkstra algorithm for on this. And our Dijkstra algorithm will return a shortest distance for each vertices. Okay, in our graph, because our Dijkstra algorithm is a single source shortest path. So, Dijkstra algorithm will return a shortest distance, shortest path for each vertices, and will return a distance value. So that means we will get, like this example, for 2 we will receive the signal in 4. Suppose this is second time, okay, in second, 4 second. And at 1, s to 1, we need at least 4 plus 5, that 9. Okay, so this is the 4 9. And here s to 0 we need 10 second. S to 6 we need 1, and then S to 7 we need 1 plus 2 3. Okay, S to 4 we need 5, and S to that 5 we need 5 plus 8 13, and S to 3 we need 6. So this is the shortest distance from S to every node. So Dijkstra algorithm will return this information 10 9 for each vertices. What is the shortest distance? So what we can do, we can say that we cannot say that, like minimum we cannot select minimum distance for any vertices. Okay, suppose if we are picking like this 7, so this is we are reaching at this point at 3 seconds, but from S to 7 we are reaching in 3 seconds, but we cannot reach other vertices in 3 seconds. So this is not the correct answer possible. Okay, so among all these shortest distance we will pick the maximum one. Okay, which one is the maximum one? So this 13 is the maximum one. At this 13 second, we can say that we will receive the signal by the all receivers. So at this 13 seconds, so this is the maximum time by any one vertex. Okay, but before that we will receive, this 4 will also receive the signal, this 3 will also receive the signal, because all have the less time compared to this 13. So this will actually receive at the uh, end of the okay, end of the all. So this is the maximum time. So this we will pick, and this is a shortest distance. Okay, so this will be considered as a that minimum time required. So in minimum 13 second, all receiver will receive a signal. Okay, and another thing, we also the Dijkstra algorithm also maintain this information, that uh, that visited information. Okay, so if any you have also, you have to also check that if all the vertices are visited or not. Okay, so just check, just run a loop and check if all vertices visited equal to true. If any vertices are visited equal to false, then return a direct -1 without checking any maximum value of the shortest distance. So these two logic you need to apply here. So in Replit team, that Dijkstra code is given for this problem. That Dijkstra, you can see Dijkstra code is given, already given to this. But here you need to do something, some pre-processing, when if you want to call this Dijkstra algorithm. Okay, because this Dijkstra algorithm is working on a adjacency list, but you have, what you have information, edges. Okay, you have the edge information. So here you need to convert this edge into a adjacency list first, and then after that you can call this Dijkstra algorithm, and you will get a result, this distance. Okay, return a distance, and you can also return a that visited dictionary. Okay, you can update this code. If this is not updatable, so what you can do, you can just use this infinite things. If any vertex distance is infinite, then you can consider that as a that is not reachable. So you can also return the answer based on this infinite value. Okay. Otherwise, suppose this code is not given, Dirichlet algorithm code is not given, so there at that time you have to write this Dirichlet algorithm, or you can also write the Bellman-Ford algorithm at the place of this. So, but for this problem, so on the portal, actually this Dirichlet algorithm is also not given. So just try to implement this at least one of the shortest path algorithm for this problem on the portal. Okay. So we have already discussed this, the concept of Dirichlet algorithm, how Dirichlet algorithm works actually. So you can see that session. Here we will write the solution for this. Minimum transmission time. Okay. So you can also try to write the solution. So now this problem is not big here. You need to just that convert this edge list into a and just make a adjacency list. Okay, and you have already seen that task is in the previous problems prefix suffix code that is already done. The same things you can do here. Okay. Or okay, so this is now with problem statement. Yeah. So you can also make this as a directed graph, so there's no problem because we can apply the Dirichlet algorithm on any type of graph. Dirichlet algorithm on directed or undirected. So you can convert this into a directed graph. So that means if you have this UI to VI, and you have to make this as a directed graph because this edge is representing that UI is the source, VI is the destination, and WI is the uh, travel time. Okay, so this is that means this is directed. Source and destination is given. So source node and target node. If any vertices have like reverse edge, so VI, comma UI, comma WI, so then we will make it directed as. So here you can see this 101 in the sample graph. That means you can move from 1 to 0 with travel time 1. So no reverse information is given. So that means this is not a undirected graph. This is a directed graph. So convert this information into a adjacency list and call the Dirichlet function. After that, receive the output and check the output. Okay, so this is the task for this. So how we will convert that? So we will create a adjacency list. So let a list that is actually a dictionary. After that, we will run a loop because we know that how many vertex we have. So we have the vertex n. Okay, and we will just run as a 0 to that's n minus 1. So we will run a loop. So for I in range, what happened? N. Okay, and after that we will just call this function a list. We will create a list for each source. So I want to empty list, and after that we will run a loop from this travel time edge. We will read each edge. So for that u comma v comma that d. Okay, so this is distance in travel time times. And we will just add this information into our adjacency list. So that a list. So here u is a source. So that u dot append. Okay. And in the append, just make the one tuple, and where the first value will become v and second value will become d. So now this become a adjacency list. So this is the part where we are converting edge list into a adjacency list. Okay. After that, we will call this Dijkstra algorithm. So you know that Dijkstra algorithm require that adjacency list and source vertices. So call this function. And we will receive the output from this. Okay, so one information we have this distance. So I'm writing dist comma max dist. That is actually infinite things. What is the infinite value? So I'm writing inf value. Okay, so now this is the first thing, and so our adjacency list name is a list, and s we have already. Okay, yeah. So this is now our call. So we will get the output, the shortest distance in our distance dist adjacency list. So this is actually adjacency list, not sorry dictionary. Okay. Now just check the output. You can run a loop, and you can figure out the maximum max dist, or we can see that max time equal to 0, and after that for each source. Okay, so that each vertex for v in that dist hotkeys. So that means we will compare this. So if dist dot that s sorry v is okay, so that is contain the distance. Okay, v, this value is greater than our max time. So max time, then we will update this. So max time equal to new. Okay, so this dot. Okay. So now after that, this is now updation, and we will check that our max time is so that inf value we also have. Okay. So if our max time is now reached at the infinite value, if we are getting this infinite value, so we will check this if our max time is equal to that inf value. So that means if any vertices are not connect, so we will get the distance for that vertex as a infinite. Okay, so if our max time is reached at this infinite value, so we will return a answer -1. Otherwise, we will return the max time. INF value. Okay, so this code will be written outside of the loop. So now this is the code you need to write in this. So this type of question is also asked in the exam. Suppose if additional task is required, so algorithm will be available in the code. So here this algorithm is given. You need to just do this task and check the output. Okay. So let's check this. Is there any problem? Okay, so now this is running. Let's see this on the portal also. Okay, for portal, the Dijkstra algorithm is also not given. So we have to copy that code. Okay. Yeah. So any query in this solution? Anyone? Second problem.
No, sir. Continue.
Okay. So now let's check the third problem. Five. This one. Okay. Again, some detail is given here also. Some code is given that returns some information, and you need to do some task. So what is given in this problem statement? An airline company. Okay. So an airline company has flight operational in n cities labeled from 0 to n-1. Write a function base fare, flight route, source, destination k. Okay, so these details are given. So in which you are given a weighted adjacency list flight route. We have already discussed this. Source is a source vertex and destination is a destination vertex. And k is also given. So what is this k? K positive integer. That function returns the minimum cost and flight route in the format. Okay. So you need to return the output in this format. So that means the minimum cost for this source to destination, and that means source and next stop, destination. So this is the path actually. Okay. So you need to return a minimum distance from source to destination as well as the path. And from source to destination with at most k stop. Okay, so you can use at most k stops in between source and destination. Okay, where the source and destination are not included, so do not count this source and destination for the stop. So if there is no such route, return string not found. So here some constraints are given. Otherwise, this is a straightforward shortest path algorithm if this k information is not given. So you need to figure out the minimum shortest path. Okay, so shortest path between source to destination. Here information is given. You can only use that number of stops maximum. Okay, so for this, let's understand by the graph. So suppose if you have one graph like this, so A, and you have this B, C, D, A, F. Okay, so I'm taking some constraint based example. So like this, weight is given, so 5, 10, 20, 30, 40. Okay. So here, if suppose we are asking the shortest path from A to F. So A to F. So this A is now source, and this is as is destination. And some k value is given like this. You can only use at most 3 stop in between. So then you cannot return the shortest path. Suppose if your algorithm have this Dijkstra algorithm or any algorithm if you want to apply here, so that algorithm will return a shortest path. Okay, and this is the only one possible path your Dijkstra algorithm have. Okay, this. But here you are getting how many stop in between? So 1, 2, 3, 4, 4 stop. But the constraint is given like that. You can maximum use 3 stop. You can use 1 stop, 2 stop, 3 stop, or 0 stop. Okay, so this is maximum value, but you cannot use the 4 nodes in between. Okay, so these constraints are given. So among all path which you have this constraint fulfilled, which one have the minimum distance? That minimum distance. Okay, so you need to figure out all possible path from A to F in your graph where this constraint is satisfied. So that means your path maybe have direction like this A to F. Okay, so what is the distance for that? If your path have one vertex in between, so what is the distance for that? If your path have two distance, that two vertex in between, then what is the distance? So this is not a straightforward Dijkstra algorithm based question. So because of that, some code is given. So that code actually we have used in previous week, that related code. So that code is actually written a all possible uh, paths. Okay. So you can see this code is already given, find all paths. So this function find all path. So where we will provide this adjacency list, source and destination. And this function will return the all path. This function will return all path, that list, where this list will contain a all paths possible. Okay. So you can see following function return a list of all paths from S to D. Format of return list is like this. So list of list. So a list contain another list. So where the path is given. So like AST, S to this one. So this path information is given already. So this code is doing this task. You no need to figure out all possible path here. This function will return. After getting the all possible path, your task is to figure out the path which have the uh, this constraint fulfilled. That means at most key stops are there in all. How many paths are available with this constraint, and among all these paths, which one have the minimum? Okay, and you need to do this task. Okay, so this is the output. This type of the output you have. So this means S, and after that, suppose you have this A, comma B, comma C. So this is just a sequence of vertices in the path. So this type of all possible paths that function will provide without checking any k condition. Okay, you have to check this k condition. So in your logic, and you have to filter the path that follow this condition.
So can we do like length of the list that we will get after that is
That you
less
can
than or equal
apply.
to k?
That you can check. Yes, correct. So you can check the return output path list. So suppose k value is 3. So 3 means you need to add two more. Okay, so source and destination. So that means 3 plus 2, 5. So after when you're getting this list of paths, so just check the length of the each list. If you have the length of the each list is less than or equal to 5, then consider that. Okay. But after considering this all path, then you have to figure out the minimum distance for the path. Here distance is not given. Here only path is given. After getting the path, you have to calculate the cost for that path in your graph. That you have to do by your adjacency list information. And after that, you have to compare all the distance, that cost, that total distance, and you have to return the minimum distance answer, and as well as the path. Okay, suppose you are getting like that P1, P2, P3, P4. Okay, suppose algorithm is returning 6 paths. Okay, total 6 paths, but these 4 paths is actually following the key constraint. Okay, so among all these paths, you have to return the cost for C1, C2, and C3, C4. So S to D, what is the total cost? And among all these costs, you have to return the minimum cost. Suppose this C3 is the minimum, then you have to return this answer C3, comma this path. So this is the format required. Okay, so minimum cost and then path in the tuple format. If any path is not available with this k constraint, k stop constraint, in that case you have to return a string not found. Okay, so after filtering, suppose you had received some path and you are filtering that which path follow the condition, and you are not getting any path, so that means you will return a minus, that not found message. So here actually the main task is to calculate the cost from adjacency list. Okay, Otherwise, the remaining path is fine. You can simply receive the path information by the function, but after that you have to calculate the cost. So you have to traverse the list all vertices from source to destination, and then you can calculate the cost. So yeah, this function you need to write the code. So first thing, so what we will do, let's start this. Okay, so let's L equal to that we will call the function find path, this one. Okay, so here we will pass the value. So flight route is the first list, adjacency list. Source is now this one, and destination is this one. Okay. Okay. Yeah. So now we call that function ever function, and that function will return a all path. And what we can do, we can directly check the first thing. If L is not equal to that empty. So L is not equal to that empty list. So then we will check. Okay. In else condition, we will return a not found. Because if our algorithm is not returning any path, so that means no path is possible. No path we found. So we will directly return the answer in else condition. But there is a chance if our algorithm maybe returns some path, and after that, that path is not following our constraint. So there is another condition also we have to check to return is not found. So we will check this inside this function. Okay. So if L does not equal to empty, so we will check that cost, or we can assign the cost. So we need to find out the minimum cost here. So what we can do, we can assign a maximum cost value as an infinite value, and we can read that. I think that is given in code. Okay. So what we can do, we can take some cost equal to, and this INF. I think this is the way to initialize the infinite. Some infinite value we want to initialize here. Okay, so cost we are assigning a infinite. Okay. Or float. I'm not sure that. Okay, so let me check this. So after that, we are initializing our cost with some maximum value. Okay, you can do something which is we have already seen in the Dijkstra algorithm. We will just take some maximum distance, and we will multiply that distance from each vertices in our graph. Okay, so we will figure out the maximum distance in our graph, and we will multiply by the number of edges. So that, and we will add +1. So we can make the infinite value in that way. Otherwise, we, or in Python actually provide the shortcut directly infinite value. So we can also use that. And after that, we will just create a one total roots. So it's empty. And after that, this is roots is actually for the our output. Okay, total output. And we will just store the final result in this. Initially, this is empty. So now we will just read all the paths. So for path in our L. Now this is the path. And after that, we will check this length things. Okay, so if our length of that path is less than or equal to, we can consider that, okay, so equal to k plus 2. So why this k plus 2? Because k is the intermediate nodes and 2 are the source and destination. So that condition we are taking. If this condition is satisfied, then we will consider that path in our checking purpose. Okay. So next thing is we will figure out the cost. So cost, how we will calculate the shortest path cost. So like S cost. So that means we will figure out the cost for this path. So we are initializing with 0. S cost is 0 initially, and we have to traverse our that adjacency list here, and we have to check, because this path, what this path is actually contain S comma A comma B comma D, like this. Okay, so we have to figure out the path, like what is the distance from S to A. So what edge we have from S to A, then A to B, then B to C. So for each edge, actually we have to figure out the distance, and we have to add the distance in our path. So we can run a loop. So here that we have to run a nested loop. So for I in range, so for each vertex, actually we have to, this is for each vertex in the path, 0 comma length of path minus 1. Okay, so how many times we need to run this? Because what is the length of our path? So because that we are running this loop. Okay, so how many vertex we have? And for each vertex, we have to, each time we have to figure out the path. So for j in phyllite root, and inside this path, and path contains what is the value of I. Okay, so this I. Okay. So if path I plus 1 is equal to j okay, j0, so what zero source. I okay, so I actually, yeah, this is the starting index. Actually, what is the value of at 0 index? We are looking at that value. So for j in flight root path, so this we are using as a key. So for this, that means if first vertex is source, so that for source we are looking that j. So this j is just a what is this? Just a, this is a value for this source in flight route. So this j is a list, okay, that contain that our destination things. So you know that in the problem statement, yeah, this is the things. Suppose this is the source vertex, then we have the tuple, where the 0 index we have this destination index, and then price. So we need to figure out this price value if we are getting this source vertex and destination vertex is the next vertex. Okay, so we are checking this condition. If suppose our first vertex is S and A, then we are looking this. Okay, so for S key, then we are traversing this. If our this destination value is A, okay, so then we will read this price value for this. Okay, so we are looking this thing in our code, and this main function. So you can see, and we will check this for each vertex. So that means I is the 0 vertex. Then we will check for I 1 vertex. So 1 to 2, 0 to 1, then 1 to 2, 1 2 to 3 in this way. And this will run like as a length of the path minus 1. So we will check for each vertex in the path. So now j in flag. So this j is now copying the value each tuple. Okay, that is j is now each tuple that is representing a connected vertices. If path I plus 1, okay, so in path second vertex, so I plus 1 vertex is meshed with the first tuple value, that is destination. So we will read the cost and we will increment our cost by the second value of the tuple. So here we will write like cost plus equal to then j1. So j1 value, j is a tuple where the first value is the destination and second value is the cost. So we will add this. So now in this way, so what is missed in this path of path? Okay, so sorry, PTH. So now this is done. So we have added this cost. So now after doing this, calculate this cost for
Sir, aren't you adding J1 or J0? J1, correct?
J1, yeah, J1, correct. So this is the cost. So now we got the cost, and this cost we will compare with the that maximum cost. Okay, so this one, actually this one we will get the final output, and this roots we will get the that corresponding root path. Okay, so now we will compare this if our that s cost, current path cost, is lesser than total cost. Okay, so because we are figuring out the minimum cost, that minimum that is COST. So we will assign our cost to S cost, or we will also do one more thing. So we will append our root, or we will just assign our root equal to that PTH. Okay. So this, in this way we will check this for each path, okay, which we have inside the L list. So we will check this for each path, and after getting the path total cost, we will compare that cost with the maximum previous one, smallest previous one. If we are getting more smallest, then we will update our cost, final cost, and we will also update our final path. Okay, so in this way, this loop will work, and we'll get the minimum cost path. Okay, and this is the one thing. If we are performing this loop and we are not getting any root, so this initially this root is empty, you can see that this is the initial empty things, then what we will do, we will just check this condition out of this loop. So if our root is equal to empty, that means this is not updated. So that means we did there's no path available with the k constant. So that we will just check this and return a message not found. Okay, otherwise we will return the information. So return that cost, comma, that root. So this is our output, and we will also fulfill this that one more condition corresponding to this first if. Okay, yeah, else here return not found. Okay, so this last message, okay, oh sorry, roast. So this last condition is for corresponding to T, this one. If we are not getting any path from the algorithm, that code, then we will directly return not found. Otherwise, we will check all the path, and if we are not getting any path which fulfill this condition, then by this condition we will return. Okay, so this is also coming from else part, sorry. So this we will return as a answer. So this is the part you need to do for this problem. So let's check this. I think repeat. Okay, so past failed. Okay, so we are getting some error local variable as cost reference. Where line number 7. No, why they say I'm not local variable as cost reference before assignment. We have already used here. Invalid root path I. If none of this, okay, we are doing something wrong. Okay, so we need to write this complete code inside this. Now this is the for loop. Okay. Oh, now other field. Okay, spell that not found. What is the output required? Small f. Okay. So that will update. Okay, so yeah, this is the solution for this problem number 3. Okay, any query in this, any part in this code? We are not getting any part. So this is the main part here where we are checking the cost. So like what we are doing in this, so suppose we are getting the path like this. So we have the source vertex like 1 to 5, okay, and now we are getting the path like 1, 2, 3, 4, 5, like this, okay. So what we are doing, we are just taking the each value, so like 0 index to last index, this one index, not the last, only this index. So we will pick this index 1 and we will check. So this is the source actually, and in our dictionary we will check what is the corresponding edge which we have connected through this, okay, like this. And each vertex we have 2 value, so d1 and this dash d2 and cos2, d3 cos3, okay. So in this way, for this key we are looking for we are checking if that path, so this is actually path, so if path I plus 1. So I is now corresponding representing this, and I plus 1 represent to next node, this one. Okay, 2. If this is matched with, if this 2 is matched with any value of this D1 or D2 or this D2, D3, any value. Okay, so that means we have connected, we have the edge. So we are matching this first value with our next vertex 1 to 2. If we are getting this matching, so we will add this C1 or C2 or C3 in our total cost. And after that, we will consider this as a source, and we will check the if 3 is now connected to this 2 in our record. And then we will add the cost 3 to 4, then 4 to 5. So in this way, we are just figuring out the edge 1 to 2, 2 to 3, 3 to 4, 4 to 5. And we are adding the cost. So that part actually of the code is doing these things. So this is the main part. Other part is simply comparing the previous cost to the minimum, that current cost to the previous minimum cost, and then we are updating things. So any query, anyone in this? Okay. So if there is no query, then we can release the week 6 problem also. Yeah. So week 6 is basically a binary search heap based week. And we have also discussed some improved version of the previous algorithm like this Prims and Kruskal algorithm. That, but the main contents are related to the heap. Okay, heap and binary search tree. So some the problems are also based on that. So let's discuss the first problem. And if you know the concept of heap, then we can solve the first problem. So let's move to the press the page. So first problem. So I'll discuss first and third problem. Okay, so second problem is also based on the same Kruskal based concept. So you can write a logic for that. So this first and third problem I'll discuss today. So write a function type of heap that accept a heap A and return string max if the input heap is max heap, min if the input heap is min heap, and none otherwise. Okay. So if you know that what is the max heap, min heap, okay, then you can test the condition and check based on that return the output. So you should know the clear concept of max heap or min heap. So in max heap, so for max heap and min heap, we have these two types of heap. And generally we represent these heaps by some list or array. Suppose we have the one list 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we have these value in our list. So corresponding how we can generate a binary tree for that. Okay, and that will consider as a heap. Okay, so this first value will be considered as a root 1, and after that we will traverse each node and we will fill this complete binary tree. Okay, so that means the first, this is the 0 index value. Okay, next value will come at this point, then this 1, this is 2. Now next will come as a this point 3. Okay, so that means we will fill this binary tree level wise. So this 3, now the next will 4, then 5, and then 6, then 7. Okay, and then 8. So this is a complete tree. Complete tree means we will not skip any vertex which are coming previous to this. So before 8, any vertex is not missed in the each level. So that is called as a complete tree. So we cannot make this tree like as this one. Okay, so we cannot skip this. Okay, before this last one. So this is a complete tree. We are representing by a heap. So you can the corresponding index you can consider as a 0, 1, 2, 3, 4, 5, 6, 7 in our list. Okay. Now this is a heap. And what is max heap and min heap? So max heap is if any parent node value is greater than to their child node. Okay. If we compare the parent value to the child of that parent, so this parent should be greater than to the child nodes, or maybe equal to the child nodes, but not less than. Okay, so this property should be fulfilled by every vertex in our tree, any node in our tree. So you can see, and same things for the min heap. So that means if every node contains if every node is smaller than or equal to their child nodes. Okay, so that is called as a minimum heap. So in this tree, if you see that what is the value of each node, so this one is smaller than this child node 2 and 3. Okay, so yeah, this is fine. Same things. So this we are checking here. So this is now fulfilling the min heap condition. So parentage is smaller than the child nodes. Same things we will check for this part. Now parent of this 2 is smaller than 4 and 5. Okay, so this is also fulfilling the min heap property. So this part is also fulfilling the min heap property because 3 is lesser than 6 and 7. And this part is also fulfill the minimum heap property. So 4 is less than the 8. So if all part fulfill the property of min heap, then we can say that this is a min heap. Okay. If all part fulfill the property of max heap, then we will consider that as a complete max heap. Okay. Otherwise, if any that tree is not fulfilling the complete max tree or min heap tree, so we will just consider that as that is actually a normal heap. That is not a min heap or max heap. So we will return as a none answer for that. So now this is the things. Here you need to check these things. So where from you can start? So you can start from, so suppose here in this example, you have this total number of 8 vertices, that 8 elements, and what is the last parent you will consider for? Okay, so what is the last parent which have some child? So how you can calculate this? So you can calculate this by a total number of vertices, like 0 first index plus last index, and just perform the this flow division. Okay, so you will get the 3, and 3 you can use as a first parent to check. After that 3, then 2, then 1, then 0. So you need to check these parents. Okay, and what is the left index, what is the left child, and what is the right child, because we are getting this input list. Okay, we are getting this input list, we are not getting this tree, but we will consider this input list as a tree. So how we will figure out the left child and right child? So we will start from this vertex. We will get the first parent node by this total number of 0, the initial index and last index by flow division by 2. Then we will get 3, and we will start from 3. So what is the left child and what is the right child? Okay, so suppose this is a I equal to 3. So you can consider that the left child will become as the 2I plus 1. Okay, and right child will always come as a 2I plus 2. So that formula you will calculate to find out the index. So that means in this list 0, 1, 2, 3, 4, 5, 6, 7. So you need to start from this 3 vertex, and you will compare this value third index to this 2I plus 1. So this means 2 into 3 plus 1. So 6, this one. Okay, and no, plus 1, sorry. 2I plus 1, that means 7. And you have to also make one condition to check this. If 2I plus 2, when you are checking this right child, okay, when you are checking this right child, just check that this 2I plus 2 is less than of the last index of the vertices. If this value is coming less than or equal to, that's 7. Then only check this, compare with this value. So this compare this 3 value with that right child value. So you have to maintain this condition. If this is satisfied, then check to the right child. Otherwise, you will get the out of index error. So suppose for 3, there is no right child, but you will get the index 2i plus 2 equal to 8. So you will get a index error. So to prevent this index error, just check this property in your code. If this is satisfied, then only check. Okay. So now this is the things. Now you need to compare each value from for 3, for 2, for 1, for 0. If all satisfy, suppose this vertex is satisfy min, if this is also satisfy min, if this is also satisfy min, if this is also satisfy min, then return as a overall min heap. Okay. Same if this is a max, if this is a max, this is max, this is max, then return a max. If any is max and anyone is min, so like this, in this way you are getting, suppose first is max and second is min, then return in an answer, because that is not fulfilling any one criteria for each vertex. So this is the concept of the checking min heap and max heap for this problem. Okay, so here you can see this code is given. So this is a min heap, this is a max heap, and this is not a min heap or max heap, because now you can make the tree for this and you can understand this, why this is not a max heap or min heap. So let me just create a tree for this. So 1, 5, 4, 7, 6, 3, 2. Okay, so this is also important for the quiz paper also. Okay, so some suppose list is given and what is the type of that heap. So you can check this from this vertices. Okay, so this is the last parent. So 4 is greater than 3 and 2. So this part is actually representing a max. Now 5, this is now 5 is smaller than 7 and 6. So this part is representing a min. But so that means if you are getting 2 different type of part, that then return a null answer. Okay, so this is not fulfilling any particular min heap or max heap. So in this way, you can write the code for this. So how we can write the code for this? So type of heap. So let's write a function. Type of heap. Okay, and we can also create a separate function for to check. Okay, so like def to check min heap. Okay, and we will receive the list, or so what we are getting a. So let's follow the a. Okay, so this is the one function we will write code here, and another function we will write, sorry, def max heap for a. So we will call this function and we will check if this function is returning a true. So that means output is a true. So, and we will call this function from our main function. So now from this first min heap condition, okay. So for I in range, so that range we will start from len of a. So len of a, okay. Then or we can write like as a 0 plus 0 plus that last index, or we can also directly write len of a minus 1, a minus 1. So this is the value. So suppose we have 8 elements, so 0 to 7, okay, and then floor division 2. Okay, so this will be the range. So 0 to this value. Okay, this is the 3. No, we have to also add plus 1. Yeah, because this is the range things. Plus 1. So how many loops now there? So this is the first. Okay, so this is now divided by 2 and part is there. Okay, this one, and plus 1. Okay, yeah, this is the final range. So suppose we have this range and we are getting 3 plus 1, 4. So that means range will run 0, 1, 2, 3. And okay, so okay, so you can also run a reverse range, or you can also run a that 0, 1, 2, 3 like this. And for each vertices, now this is the loop, and in this loop we will check this condition if that a of I is greater than. So we are checking for min heap. So we will check this condition and we will satisfy the, or we can also return like this: a1 ai is less than equal to that. So what we will write here in this index for left child. So that is actually 2 into I plus 1. Okay, this is the one condition. If this is satisfied, and second condition we will write as a two condition. Okay, so okay, this is okay, so the same things. This one plus 2, and next condition is this 2i plus this one should be less than equal to len of a minus 1. Okay, so len of a is now, just suppose 8 and then 7 is equal to, okay. Now if these three conditions are satisfied, then we will return answer 2. Okay, so I hope this is clear. So we are comparing our element ai. So ai means that we are starting the comparison from parent. If that parent is less than equal to left child, okay, so there is no problem with left child. And if this is also less than equal to right child, and our right child index is less than equal to len of a minus 1, last index, so then we will return the true. Okay, so we will call this function. If we are getting true, then we will return the answer. Otherwise we will return the answer false. Okay, so now this is for min heap. Same things we will do for the max heap, and here the condition will be different. So this is a max, and same here, max and 2i plus 2. This is okay. Yeah. Okay, so this is for max heap. Okay, so now these are the two functions. Now from here we will just use if else if. So this thing. So if our min heap, so we will pass the first min heap of a is equal to true, then we will return answer that min. Now second condition, if max heap of a is equal to true, then we will return max. Okay, and the last part, if both conditions are not true, we will directly return none. So now these are the function to check the what is the type of heap. Okay, let's check it is working for all test case or not. Okay, so this is failed. Let's see. Unmesh, some bracket issue is there. Where, yeah, this one. Okay, so corresponding this is one. Okay. Where we have put a additional line of this completing here. So first thing this one and this one is divided by 2, so it will complete. So let's make this separately. Okay, list out of index we are getting. Oh, 2I plus 2 is less than or equal to ln of A minus 1. Why are we getting this? Oh, seconds. 0, 1, 2, 3, 4. So here 0 plus 4. Okay. So we have to reduce one more. So this ln of A minus 1, 7, and then we have also reduced one 2. Okay. Min, and we're getting none. So which we are getting this. What is this? Okay, this was the none. Okay, okay. So yeah, this is little bit because if at any time we are getting this condition true, so we will return direct answer. So here we will change this condition. If any time if our condition is failed, then we will return false. Otherwise, we will return true. Because we need to check if our all that parent have satisfied the condition. Okay, then we will return only true. So in this case, let's check replace this condition. So like this is greater than, this is again greater than. Okay, and then return false. So we can return false if we found any time condition are not fulfilled. So false, and we will return here as a true. And same things we will do here. So we will return the reverse condition. So we are checking opposite condition. If you found any opposite condition true, then we will return as answer is false. So false and then true. Okay. Yeah, now this is working. Okay, so this is solution for week 6 problem 1. Any doubt in this? Anyone? This code? No, sir. Okay. Okay, so let's move to the last problem. So I'm moving to the third problem. So just second problem is basically similar to your that Kruskal algorithm based problem. So that union find. Okay, I'm opening this problem once. Problem two. Yeah, okay. So write a function find redundant edge. Yeah, find redundant edge, then accept an edge list in increasing order of the edge weights, where all edge weights are distinct and the number of vertices labeled from 0 to n is connected and right graph. The function return a list of redundant edges in increasing order of the weights. So by removing this edge, the graph should remain connected with the minimum total cost. So you can see here edge is given, and we need to figure out which edge we can remove from this. So after removing all the edge, we should get a minimum spanning tree basically. Okay, so here we are just returning the edge which actually will not including the MST, minimum spanning tree. So this is just a reverse things. We have already done the Kruskal algorithm. You can try the same. If any edge is not including in the MST, just consider that as in the output list. Okay, so this is the only things. So apply the same Kruskal algorithm logic and just change this condition. So this you can do. Then move to the problem third. So yeah, this problem is so this is binary search based problem, and in this problem, what is given? Write a function find kth largest. Okay, so kth largest node, that value, root is given for the tree, and k value is given. Okay, that accept root as a reference of the root node of the BST of n elements and an integer k, where the k is less than equal to, that greater than equal to 0 and less than equal to n. Okay, so first largest means the maximum value in the binary search tree. Second largest means second maximum value. So the function should return the kth largest element without doing any modification in binary search tree. The complexity of the solution should be in the order of big O log n plus k. So log n we are just considering that our binary search tree is balanced. Okay, so that we are considering that height, actually you need to traverse at least the full height and then plus k also. Okay, so just consider this in this question, our binary search tree is a balanced tree, and you need to figure out the maximum second largest like this. So in binary search tree, you know the property of binary search tree, where the each node on the right side is actually greater than, and each node of the left side of any node is actually smaller than. So we have this property with the every node. So like we have one binary search tree, so we can take one example. So 15 and this 10 and then 25. This is 20, the 30, and this is 8. Okay. So now suppose this binary search tree is given. So you can see the property 25. So just check this. So 15. So all nodes which are connected to this left side should be smaller than this. So this is also a main property, as well as the we will also compare the left child, but also the left subtree part should contain the smaller value compared to this 15. Same things, the right part of this should be contain all value which is greater than this. So this is one property we need to check. Other property, the child. Okay, so that the right child of this 15 is should be greater than this 25. Okay, and same things, left child should be smaller than this. So we will check this property with parent, left child, and right child, as well as the parent and left subtree or right subtree. So this property should be fulfilled for the binary search tree. So here you can see the all value on the coming on the left side are smaller than 15. Okay, and value which are coming on the right side are all greater than. Same things you can check with this 10. Okay, so all smaller value which are coming on the left subtree are smaller than this, and right subtree are greater than this. Same for 8. So left is small, right is big. Same for 25. Left is small, right is big. So this property is fulfilled by the binary search tree. Now the question is, this root is given. Okay, and you need to figure out the kth largest. So if k value equal to 1, so you need to figure out the maximum element. So you know that in binary search tree is a ordered tree, and where the elements are arranged in some order. So in binary search tree, maximum element will always come to the right most child. Okay, so what is the rightmost child position? That will be the maximum element, because if you check this, this is the right child will be the greater than this, and the if you have any other right child, that will be the greater than this. So the maximum element will always come at the rightmost child position, and smallest element will come at the leftmost child position. So what is the last left child? So that will be the minimum. This is the minimum one in our all element. This is the maximum one. So if you can traverse, suppose if you are at root, just traverse right child. Okay, so what is the right of 15? Just move this. Okay, what is the right of 25? Just move to the right. If right is available, just move. If right is not available, just stop and return the answer as a maximum. Okay, so in this question is asked that k equal to 1, then you need to return answer to 30. If k equal to 2, the answer should be 25. If k equal to 3, answer should be 20. So binary search tree is given in this form. That means here this is not given in the list or any type of, here binary search tree is given. Okay, so now you need to figure out, you need to return this answer. One way to do this is you can traverse the list by in order traversal. Okay, in order traversal you can, so this is actually recursive implementation in order traversal. What we can do in the in order traversal, we first move to the left side, so that means recursive left. So that means we can say that we will just suppose we are traversing in order. So what we will do in order, we will move to the left child first. Okay, then second step is print the node, print the current node, and third step is in order on the right side, right child. So these three steps actually, where the two steps are recursive call. Suppose we have the in order of the root. This is the first call. Okay, suppose this is a function def in order root. So what we are doing when we are entering inside this, if our root is not empty, okay, so then what we will do, we will check, we will move to in order L. L means this root dot left. Okay, so we can write like this, so root dot left. Okay, same here. So root dot right. So here left means left child, or right means right child. So we will call the same algorithm on left child. So suppose if we are at this position, so we will move to this position and we will call the same algorithm in order. Okay, then from this again we will move to left, then again we will move to left. Now there is no left, then we will move to the second step. Okay, then print. Okay, so print current node. So this one node will be printed. After that, next step is in order right. So there is no right. Now this all three steps are complete at this point. Now we will move back and then print current node. So this node is there 8, and then right is there. We move to right and no left. Then print this 9. So in this way, if you just apply the dry run of in order traversal, you will get a sorted list. Okay, so sorted list of elements. So like 1, 8, 9. After that, you will get 10, then 12, then 15, then 20, and then 25, and then 30. Okay, so you can apply this in order traversal. In order traversal will return a sorted list of elements of the binary search tree, and after that you can directly return the kth smallest or kth largest element by this list. Okay, this is a shortest. If you're finding out kth largest, so just return the that k value. So this is second, so just return a -2 index, this value. This will be the answer. Okay, so but this is taking out of n time at least, n plus k, we can see that. Okay, what we are doing, or we can say that only n. Okay, so we are traversing all the elements first. After that, we are directly returning the answer. But we can we do with lesser complexity if our k is small? Like suppose if we are asking k is equal to 1, so just traverse the this side only. Okay, so what is the height of the tree, and just return the answer. So can we write some solution code in this way? So we can return the kth value in log n plus k time. Okay. If our k is equal to n, so then it will become equivalent to the order of n complexity. But if our k is less than, suppose if k is 1, k is 2, then it will work as a that log n plus 1 or 2, like this time. Okay, so this is our purpose. So how we can do this? So one, let me just discuss the solution also. So here the solution we can do, we know that maximum element is coming on the rightmost child of this tree. So we will traverse first this rightmost child, and we will reach at this last maximum element. Okay, and suppose if our k value is given as a 3 or 2 or maybe anything. Okay, and after reaching at this position, we will return. So we will just use a recursive call, and after reaching at this last position, and then we will understand that this is a maximum, and we will take one counter, and after reaching at this maximum element, and when we will return, there is no rightmost child. That means we will return back. At that time, we will increment our counter. So that means when we are leaving this node, this maximum node, then we will increment our counter as a 1. So initially this is as 0. So this counter will represent as a which, this node is actually representing a which node, the first maximum, second maximum, like this. Okay, so in this way we will return back. Okay, and after returning back, same things we will do. We will just we will check this side also. So 25, this is the parent of this, so there is no rightmost. If any left child is there, so what we will do, we will check the left node first. If any left is there, then we will move to left side. Otherwise, we will move back to the parent node. So after any this recursive call, if we have left child, so we will move to left child. We will call the same recursive call on the left child, and then we will increment our counter again, same way. So after every time when we are incrementing our counter, we will check that if our counter is reached to this k value. Okay, at that time we will stop the process, stop the recursive call process, and our algorithm will return back from there. Okay, so in this way we can write the code for this, but we have to write the recursive code for this. So same way for the in-order traversal, but we will only traverse one side to the depth, maximum depth from the right side. After that, we will return back only kth depth to identify the kth largest. So how we can write the code for this? So let's write the solution. So this function is given as a suffix code. Okay, so we need to write the code here. So find the main function we need to write. And this t, okay, so this t is as we will consider as a root. This is a root, and from here, so because we want to write a recursive call, So we will write a separate function for that. So that def pth largest, and inside that we will only pass the root. So what root we are passing, and from the main function we will call this recursive function once from the root, and we will also assign some that global counter. So we will maintain a global counter here. Okay, so we will use some count. So count equal to 0. So this value we are assigning as a global, and after that we will write like this. We'll call this function. Okay. So that recursive function. Sorry. And this is t. Okay, and we will also use some global result. So we will also maintain a1 result variable. So result is just a maximum, that kth maximum value. So initially we are setting some any infinite value or something, so negative infinite. So I'm taking negative -1. So just assume that this -1 is not there, or you can take negative infinite value. Okay, so count is this is set, and inside this recursive function, so let's we will make this, we will use this variable count and result. So we will make this as a global count comma result. Okay, so now after that we will write a recursive call. So we will move to write most child first. Okay, so if our root dot write does not equal to none. Okay, so in that case we will call the function to the right child. So same function we will call kth largest kth largest root. Okay, it is okay. So this is return, this is here we will return a result. Okay, so this is just a recursive, this is not a direct recursive, this is indirect recursive. So from kth largest we will call this function and we will change the value. So this, if this is true, this is not, then inside this we will call this function to t dot write, not t here. So this is root, this is root dot write. Okay, so that means the same things from the kth largest. If our write is not empty, then we are calling the same lower function, and we will pass at the place of root, we will pass the right of the root. Okay, so that will become a new problem. So that means we are starting from the again same thing. So this is indirect, and after this is a call, and we will increment our count. Okay, so yeah, this is a recursive call. It will reach at the last node. So because this is a recursive, so every time we will check the right node, and if this is not equal to none, then we will move to the right. So once this function, this step is completed, we will increment our counter to 1. And after that, we will check if our counter is reached to the k value. So co count is now equal to that kth value. So at that time, we will set our result equal to what is the value of that. So that is root dot value. Okay. So root dot value, we will set this and we will write the return statement. Yeah, so return. So that means we will not call this function recursively. Otherwise, if this condition is not true, then we will write a call on the left child, because we have to move to the left child. So that means we need to write this t root dot left comma key. Okay. Yeah, so this is the recursive or function only. So you can see what we are doing. We have set this count and result as a global variable. We are moving to the right child if we have right child. Okay, so inside this condition, if root dot right is not equal to none, then we are moving to this side. And after reaching at the last node, then at the time of return, okay, so at the time of return, we are performing these steps. First, we are incrementing our count. Then we are checking if our count is equal to k. If we are getting this condition, we will directly return from here. If this is not equal to k, then we will check this also. Okay. Find kth largest root dot left. If any left child is there, then we will move to left also. Then this is again a new problem, so it will also increment our count. So in this way, from the rightmost child, we will just visit all the vertices and we will also add the counter. So that first largest, second largest, third largest. At any point we are reaching at the kth largest, so we will stop the process and we will not call the recursive. So okay, at this point, if this condition is satisfied, we will directly return back. Okay, so our recursive call will stop here. Okay, and we will return back. And then at the time, what is the value updated for result? Okay, so that node value we will return finally from this here, return result. So that will be written as a result finally. So you can see, let's test this. Yeah, this is working. So this is a recursive implementation, and you can try your logic also. Otherwise, this if this, complexity constraint is not there, then you can simply traverse by the in-order traversal and you can return the answer. So for this binary search tree, you should at least know the traversing process, that insert process by in the code, which is discussed in the big 6. And try run, you should also know how that perform. So suppose any binary search tree is given. So what should be the in-order traversal? What will be the post order? What is the pre-order? That order you should know. Okay. So that is important for the quiz. So this is the solution for third problem of week 6. If anyone have any query, then you can ask. Okay. So now today I have discussed all the solutions, all 5 problems. So now, but still after getting the logic, do not look the solution. Just try to write your logic solution on the portal. Okay. Just practice on that way. Any query, anyone? If you have any query, then you can ask. I continuously see the compressed sky art while clicking on the problems. Oh, who is this? No. Yes, Shivam, are you there? What is your exact problem? I'm unable to access all the problem. Shivam, are you there? Okay. Okay, if there is no doubt, then we can close the session. So tomorrow, yeah, Preetodeep.
Yeah, good evening, sir.
Hi,
I had
yeah,
a doubt, but not on this. I wanted a clarification on one of the quiz 1 questions. Would you take it up now, or should I ask it some other session?
No, you can ask that current quiz one.
Yes, the
Okay, okay.
7 July one.
Okay, yeah. So which question?
Question number 241. Okay, so I'll have to actually. So this is the improvement paper. So the question number might not be the same. It is the question number where there are 2 implementations of the nth Fibonacci number code given, code A and code B.
Okay. So that question actually. Okay,
Yeah.
okay, fine. So
the options were f of n equal to O of g of n and g of n equal to O of f of n. that one.
I got the point. Okay, okay. So what is your doubt?
Yeah, I got that wrong, so I could not actually get it correct.
Oh.
Can you explain how that look?
So you know that what is the complexity of each code? So one code
Yeah, I
was
thought
actually a that recursive code. Like if I
other was
remember correctly,
iterative.
yeah. So suppose if I am asking if n, so inside this there are two recursive call like this fi b n minus one
And
that plus
n-2. Yeah.
fi b n minus two. Okay, so these are two recursive call every time. But another code was just a iterative code, and where we
Right.
are just checking the previous two value fib previous -1 and -2, and we are only adding that. So in this recursive call, this is the recursive function and another one is the iterative function. So that complexity of that, this was the a and this was the b. So complexity of iterative one was order of n, big of n. Okay, but this is just like a tn equal to 2n, that 2tn, that n minus 1, so 2tn minus 1 plus 1, something like this. So this is now a that what is the overall complexity for this? So that is actually 2 to the power n.
Okay.
Okay, so if we just draw the tree for this, so tn is actually become a tn minus 1 and same tn minus 2, and again this will become tn minus 2, and then again this tn minus 3, like this. So it will expand in this way, so you will reach at the last level after the nth level. So at that time you will have a total 2 to the power n steps. Okay, so in
Okay.
that case the overall complexity of this is 2 to the power n. So now if we have these two complexity a and b, and condition is written like this: fn is for a and gn for b. Okay, so this is
Yeah,
for
so
a and this is for b.
the Fibonacci, the recursive implementation will be O of the second one.
Yes, so that we
That
can
is the
write like that:
fundamental.
gn is equal to big O of fn. We can write like this. Okay, because this one is the bigger. So inside the big
Okay.
O, we will write the greater complexity. We cannot write like this fn equal to big O gn, because then that gn will be a smaller one. Inside the big O, the value should be greater than or equal to the that
Yes.
one.
So I mean the big O concept I understand, but I was not able to reduce the actual complexity of the Fibonacci, the recursive implementation. So that is where I made a mistake for this.
Yeah,
And
so that is actually recursion based question. So recursion, you know that we have already learned this recursion many times, or that
yeah.
merge sort, all these things.
The problem is I mean even now I have issues with complexity related questions. So I made three mistakes in quiz one. One was a silly mistake, and the other two were both complexity related questions.
Okay.
So,
Another which question you did mistake? The
so
complexity one?
so there were two lists, out of which one was having numbers in ascending order, and one item can be missing. So
Okay.
the what's the
We got it.
so
So if
what
you
I
have
thought
like,
was
so like
so
1,
yeah,
2,
please go ahead, sir.
5, 6, like this sequence steps are given like from 1 to n, and any one number
Right,
is missing like 8, 9, 10, like this. Okay, so
right.
here one number is missing. So this if our list is already sorted and any one number is missing, we can apply the binary search concept in this.
So I am aware that binary search will give log of n, log base 2 of n, but what I thought was, since we don't know what to search for, so if you tell me I have a sorted list and I want to search for some number x, I can do that in log of n time. But here what I thought was we did not actually know which number to search for, because any number could be missing. But turns out we can just check the midpoint of that list, and if that midpoint is actually corresponding to the length divided by 2,
Yes,
then we can. So yeah, I asked this in the TA session yesterday, and the TA explained this. So I thought that since we don't know what to search for, we can't actually use binary search here. We'll have to do a linear search.
Okay. Yeah, so that some modification of the binary search we can apply if some pattern is there, and
Yeah.
we can figure out the pattern.
Right. Yeah. For this one, I could not figure out the pattern, and for the recursion question, I actually could not compute that complexity for the recursion part.
Okay. No problem. Just learn if you're getting something.
Yeah.
Yes. Yeah.
All right. Thank you, sir.
Okay.
Thanks.
Okay. Yeah. Okay. Then bye everyone.